This video, as the title states at the top, will be an introduction to limits, not to a formal idea of what limits are, but to an informal understanding that we can use to begin to look at what limits are. We're going to begin this informal idea with a visual demonstration of what limits mean. So we're going to start with a curve on a set of axes. So curve in the XY plane, and when we have a curve, and we'll call it y equals f of x, we can choose a point, some input value, and we'll call it a. And we know that for that input value, we can think about going straight up to the place where vertical line at A intersects our graph. And then we've determined some output value that we can find by making a horizontal line that cuts across to the y-axis that we have labeled. So the next thing that we're going to think about when we start talking about limits is not really what's happening when our input value is A, but what's happening when our input value is close to A. So we're going to be choosing values that get closer and closer to A from both the left and the right. And that means that on our curve, we're going to be starting with points that are somewhere down here, but we're going to be moving those points along the curve until they get closer to that point on the curve where we have the value for f of a, and we're going to be doing that again from both directions, approaching that point. And as a result, we're also going to be approaching some output value from both the bottom and the top, and that output value we're going to call L, and that will be the limit for this function. An important thing for us to notice or to know about this situation is that it turns out that we don't actually have to have a value for f of a. In other words, as indicated now by this new graph, f of a can be undefined, and that doesn't change the fact that when we approach a from the left and from the right, that we're moving points up closer to this now open circle on the graph, and at the same time we're approaching this same value L from the bottom and the top. So we can retain a limit even if our function is undefined, and even if our function was defined as being something completely different. That wouldn't change the fact that as we choose input values that approach A, we get output values that approach L. If you don't already have a visual like this in your notes, now would be a good time to stop and make an addition. And for the most usefulness, we might want to label what we're thinking about doing. First, we're thinking about choosing values for inputs that are getting close to A. And second, we're noticing that points are moving along our curve towards some specific place. And finally, third, we're discovering that there's some specific output value that we're approaching as a result. The next thing we want to do is write out in words an informal definition, right? Just a general understanding of what a limit means, then we can also show what limit notation looks like, and after that we can look at a few examples. So here's how we're going to describe limits for now. If the output of a function gets very close to some number L, as we choose inputs for the function that are very close to A, then L is the limit of the function as x approaches A. So there's our description of what it means to have a limit. And the notation we use looks like this. The limit as x approaches A, and I'll write this out in a second, of f of x is equal to L. So notice there was a way that we said that. All right, this is how we say that limit notation statement. The limit as x approaches A of f of x is equal to L. All right, finally let's consider a few examples. We'll start with consider f of x is equal to x over x. And this is an interesting function for us to consider because our first response might be to say, well, x over x, that's just 1. So really this is the constant function 1, and it is very close to being, let's write it out here. This is almost f of x equals 1, but not quite, right? Because in this function, if we have an input, make our x value be equal to 0, then we have f of 0 equals 0 over 0, which is undefined. And so we don't have a value at f of 0 for this function, whereas for f of x equals 1, the value at x equals 0 would be 1. Right? So those are similar, but not exactly the same. And let's look at the graph for this function then. If we say that there's 1, then we know the function is undefined at x equals 0, but everywhere else the output of the function is 1. So if we're talking about the limit as x approaches 0 for this function, x over x, then we can come over here to this graph and say, I'm going to choose values that are getting closer and closer to 0 to be my inputs. And that means I'm going to have points that are getting closer and closer to the y-axis, moving along this horizontal line with outputs of 1. And it's going to be moving right in the same way from both sides, and we're going to get close to this place where the output is 1. Even though f of 0 is undefined, the limit as x approaches 0 of x over x is 1. All right, so there's a first example that helps us understand what's going on. Let's look now at another one. All right, next up, we're going to consider a function f of x is equal to the absolute value of x over x. Now, we know that when x is a negative value, the absolute value symbol, right, the absolute value operation is going to give us the opposite of x, and the opposite of x over x will be negative 1. So for any negative values, that's what we have. So here's our 1, here's negative 1. Still, we can't put in 0 to this function. So we're going to come along here until we get to the y-axis, and then we need to note that it's still undefined here. If we choose positive values for x, then this function goes back to being like our previous example. There's no need for the absolute value operation if we have positive values for x. So we're really just cruising along up here at 1 until we get to the y-axis where we're undefined. Now, in this case, if we choose values for x that are approaching 0 from both sides, in one direction, from one direction, we're approaching negative 1. From the other direction, we're approaching positive 1. And what that means for us is that the limit as x approaches 0 of the absolute value of x over x does not exist. It's impossible for us to say where we're going as we choose x values close to 0 because we're going to two different places depending on which direction we're talking about coming from. If we're coming from the left, we're approaching negative 1. If we're coming from the right, we're approaching positive 1. If we don't approach the same place, then the limit does not exist. But we can know where we're going if we think about coming from only one direction. So we have another notation with limits that we can use, and I'll try to squeeze this in before I run out of time in this video. So if we talk about the limit as x approaches 0, and we put a little negative sign up there, that means we're coming from the left. Then the limit of absolute value of x over x is equal to something that we can determine by looking at the graph. It does approach negative 1. On the other hand, the limit as x approaches 0 from the right, so we have a little plus sign there, of the absolute value of x over x is equal to positive 1. So the limits from the left and the right exist, but the limit in general does not.